everyone, welcome to MathSpellBook. I'm your host Peter, and basically we are going to get back into eigenvalue / eigenvector problems. Hopefully you guys are having a great Wednesday. You made it to the middle of the week, so applause to you. And basically, hopefully, the weekend just feels like it's just inches away for you guys that need some rest and relaxation. Hopefully you have off during the weekend, and if not, hopefully your day off is just it's just a few inches away, so you can basically just make it to your day off and have some good R&R. Anyway, let us just get into it, shall we? I already copied the problems that we need to do. These problems are still the problems that Sascha assigned us before, so we're going to finish it up because I think these are the last two problems we have to do. So, and while I'm doing this problem, why don't you guys tell me how you guys are doing today? Hopefully you guys, or what's the best part of your day so far? I would like to know about that. Find its eigenvalues. Is it possible to find the eigenvalues without computing? Ooh. I don't know. That is a really good question. I mean, I can't think of another strategy. Let's see. Is this matrix diagonalizable? Find out without computing anything. If the matrix is diagonalizable, diagonalize it. Okay. Without computing, huh? Well, since we do have a triangle here, because we have the matrix A, choose. Yeah, I just noticed that we have a little triangle of zeros here. So that could be our first clue. Because I remember when it has this, we basically will have, so I think this is dimension 3. Because when we have this, we can tell how many non-zero columns we have. By non-zero, I mean like when we basically have, So what we know is that dimension of the column space is 3. And if I think of the dimension to the null space of A, because we have a matrix that is, so A is an element of 3 by 3. Yeah, so we have 3 rows and 3 columns. So that means it's 0. So we have a dimension of 0 for the null space. Now, if the dimension is 0, then I'm guessing that we don't have any vectors within this space. So if there are no vectors in this space, then that means there are no basis vectors in it, or hence no eigenvalues, or I mean vectors actually. So, but it still would have eigenvalues. So it would still have eigenvalues, but we just don't have any vectors in it, I think. If anyone in chat thinks I'm not stating things correctly, let me know. Because I'm trying to remember exactly what I'm learning in linear algebra so far. So question is, how do we find the eigenvalues without calculating anything? Like without doing the algebra that we were doing last stream? And hopefully my mindset is correct on my ideas. So, how do we calculate the eigenvalues without having to do any computation? Well, now the thing of it is that I don't know if we're gonna have to turn this into like because if we were to break this down into like basis vectors, we would think like A as a component here and like so, and then B plus B 6 like so, and then C now. Now, obviously, they don't have any numbers in common. The one question is that what would their values be? I mean, this one would probably be the easiest to manipulate. Let's see. Is it possible to find the eigenvalues without computing? I mean, if this triangle right here was zeros, that would make it pretty obvious, but at the same time it's like, is there any manipulation we have to do? I mean, it says without computing, so is there a way we can just like look at it and like find them? Let's take a look here. Maybe this will give us a clue. Oh, these are exercises. Diagonalization. Okay, maybe this will give us a clue. That's the thing with some math books. They have a lot of text, but it doesn't really give you a clue that much. Let's see. So is there a way to do it without calculating? Diagonalization. Find the eigen decomposition of the matrix. Oh. This might be what they're talking about. The decreasing order, the eigen... So... Okay, let's just read a little bit of this. So, in decreasing order, the eigenvalues of the matrix are 3, 2, and 1. Okay. The eigenvalues of A are the values that appear on the diagonal of lambda. So, when a 3 by 3 matrix has 3 distinct eigenvalues, it is diagonalizable. It's hard to read that one. Since it has the same number of linearly independent eigenvectors as eigenvalues. We know that the eigenvectors are linearly independent by the following reason. Matrix A has 3 different eigenvalues. Each eigenvalue is associated with the eigenvectors. So we have matrix A. It's like this. So basically we can tell by just looking at it because it doesn't look like it has anything fancy in it. So in this one, probably the eigenvalues are going to be 2, we'll put 1 and 2 here, 5, and 4. So I think that's how we'll conclude that. Okay, so now question B, is the matrix diagonalizable? Well, it has 3 different eigenvalues. Find out without calculating anything. So is it that we just look at the eigenvalues and that's it? Surely there must be something more to it. Let's see, to find the eigenvectors of A, solve for the null space of the matrix. Now the thing of it is that the question told us is like find out without computing anything. So what is the thing that indicates that it's diagonalizable? forms the basis of Rn. This is the eigenbasis. So note that only the direction of each eigenvector is important and not the length. Indeed, if E lambda is an eigenvector with an eigenvalue of lambda, so is any alpha E lambda for all of alpha is elements of the real numbers. Okay. Alright, so the eigenvector's values has 3 distinct eigenvalues. It is diagonalizable since it has the same number of linearly independent vectors as eigenvectors as eigenvalues. So these are the eigenvalues. We know that the eigenvectors are linearly independent of the regions. Each of this is associated with at least one eigenvector. And these eigenvectors are linearly independent. Recall that any n linearly independent vectors in Rn forms the basis for Rn. Since 3 eigenvectors of A are linearly independent, we have enough columns to construct the change of basis matrix. Okay. So I'm guessing you have to do this operation. So in this case, is this diagonalizable? Diagonalizable. Find out without, so I think yes. I think yes it is. I think the reason why is just because we have like 3 distinct ones and the dimension of the column space is 3. So the thing of it is that I'm concerned about this, the dimension of the null space, because we have 0 here. If it's diagonalizable, diagonalize it. Okay. So I guess now we actually have to do the computation. If I'm wrong, I might end up like wasting a lot of time, but gotta learn a lesson sometimes. I don't know why I wrote that. Okay, now we don't have to solve for the eigenvectors, we just have to solve the eigenvalues. So and since we have this little triangle over here, maybe it might make our jobs easier actually. But who knows? We'll just have to wait and see here, won't we? Yeah, so that makes it 0. And then like this. Okay. So now we will take the determinant of A minus that's minus 6, 0, 0, and 2, and 4. So this one's going to be gone. And then plus -6 with, yeah, this one's also going to be eliminated. So these two are just going to be completely gone. So this part, we're going to have 5, and that's going to be 0, so we're left with this. So meaning that yeah, looks like that's, so basically our eigenvalues are just that. Now I see why they basically try to make it like this. It makes it much easier to get rid of everything. So meaning that when we diagonalize it, we're just left with 2, 5, and 4. Boom. At least I think so. But it seems to make sense though. I mean, it feels like it makes sense to me. So if I'm wrong, you can put it in the chat, guys. Okay, let me just move this over here. All right, diagonalize matrix. Ooh. For some reason, like, all these look like they're... I mean, by looking at it, it seems like it should be like this diagonal. But I want to double make sure of that, so... I don't think this one is, because it has 2 of these. Because that's what's getting me worried here. Because if we do take the... take the determinant of this, we'll just call it A like we did last time. So we got 2 minus, that'll be 2 determinant 4, and I think these will, yeah, these will all become, yeah, so those are going to go away, so we're left with so meaning it's going to be like this. I guess that's how you diagonalize it. Now, okay, so I think that's how we do it. not too bad though. Okay, I think Sascha also added another exercise that we can do in so 2.12. So he also warned us that 2.12 is slightly harder. So, and knowing Sascha, hard is probably mean like we have to struggle with it. So I guess we might as well just do it because we already did the other two problems. So let me move this over here. Okay, so let matrix A satisfy the 0. Prove that A cannot be diagonalized. More generally, any nil-pointed matrix, i.e. a matrix satisfies AN equals the 0th vector, or 0 matrix, for some n cannot be diagonalized. Ooh, so this is a proof-based question. So, what I remember is that if we were to calculate, or at least like arrange for something like this, we would need matrix Q that's made of the eigenvectors. We need a lambda, which is basically the eigenvalues in a diagonalized fashion, and then the inverse, and also lambda has to be to the power of that. Okay, but now it's telling us that we have to prove that equals 0. And if we were to think about this, I'll just write proof just out of habit. Let equals 0. Meaning that if f is actually I should just write let A be a matrix I think we should make it square so it's like from n by n. We'll make it like that. And oops. And A to the 5th power is 0. Now prove that A cannot be diagonalized. More generally, any okay, so if we have A is equal to this, then that would mean that is equal to with Q containing the eigenvectors Hey, Grandma. Hey, Grandma Ursula. How's it going? What's the best part of your day so far, my friend? This one is a pretty interesting problem, actually. Because it's actually a proof-based problem. Had a pretty chill day, not doing quite a lot. You? Doing alright. Just trying to relax with some math. Can't complain. How's your, I guess, your PhD / fun project you're engaging with? Well, I say that because, like, you know, like, you want it to be your PhD thesis, but it could be your master thesis since you said you didn't start your master thesis yet, so. Actually, like, since your idea is, like, probably, like, I guess, like, to you, it's sort of, like, not much research is done on it, why not do your master thesis on it? Since you're so passionate about it. And then, like, if it develops further, you can make that into a PhD thesis. I think that would be pretty cool. It's like a work you've been working for, like, I mean, if it's gonna work, if it's gonna be something you inspired to do for all your life, why not make it into your master and PhD thesis, you know? I could maybe, I'm gonna connect with some professors first, though. That's good, yeah. Yeah, that's probably a good strategy, because I'm not in grad school, so I think making connections will probably help a lot, especially if the professors, like, have, like, more experience than you in certain areas. Not a lot of physics professors at my uni are deep into category theory, I think. Oh, okay. But I'm pretty sure there might be a mathematician that basically can help you with category theory then. So you can probably talk to people in the math department about it. So gotta go to the mathematics faculty, right? Yeah. Yeah, there's no helping that. There's no, resisting that, I think. With Q containing eigenvectors... and... lambda containing... oh wait, hold on. I just realized something, because if we do have, because the thing of it is we can't have lambda because we're supposed to prove that A is not diagonalizable. You got any ideas for the proof yet? How do you want to tackle it? Yeah, like, Sascha did warn me this is going to be a hard question. Like, he just basically put in parentheses, like on if you guys want to actually check out the assignment Sascha put up, it's in the assignments for stream channel. Yeah, assignments from stream channel, so you can basically check that out if you want to engage with the problems with me. But yeah, so it basically says let the matrix A satisfy just drag this down here. There we go. Because there was something text obscuring it. So let A satisfy A to the 5th power is equal to 0. Prove that A cannot be diagonalized. Actually, I have to check the first part of what I did with these exercises. Because I think the rank and dimensions are right. And the dimension of the null space, it basically would be the rank, it would basically be the amount of columns. No. It would be the amount of rows minus the rank, which is 0. I probably didn't have to write that there, but like for me it's like, because the question itself here was is it possible to find the eigenvalues without computing anything? And like reading the book that I was reading, like it looks as if, like, if you have like a matrix like this, you can diagonalize it as long as these numbers are like different from each other. But I don't know if I'm explaining that correctly. Because we did get the eigenvalues here, and then we diagonalize this. Now the thing of it is that I have to think about what makes something not diagonalizable. And I have to think, actually, like, how do we recognize that something cannot be diagonalized? Define diagonalization of A, move, let's see, interpretations, allow us to interpret the actions here. Oh, this is like the basis. Actually, I have to work on that too, actually. The first step, we can convert vector basis of... Okay. Let's see. Oh, that's interesting. Invariant properties of matrices. The determinant and the trace of a matrix are strictly functions of the eigenvalues. The determinant of A is the product of its eigenvalues, and the trace is the sum of the eigenvector. Oh, okay. That is very interesting. So basically, the determinant is the product of all the eigenvalues, while the trace is, the trace is equal to the sum of the eigenvalues. That is very, very interesting. I don't think that helps us, but it's just very intriguing to like find that. Non-diagonalizable matrices. Okay, here we go. This is something that might help us here. Not all matrices are diagonalizable. For example, the matrix has 3 repeating eigenvalues. Okay, yeah, I remember Sascha said that. Like, if it has 2... Then wait a minute. Because I remember the question we did before. It has 2 of these. And I noticed that that was kind of funny. So that means we can't diagonalize it, I think. So this probably means that we can't have it as... so this one is not diagonalizable. Yeah, I thought this one was kind of funny. Unless, like, no, I think if it has doubles like this, it can't be diagonal. Okay, so, but the null space of the matrix is B minus 1, contains an eigenvector of the transpose. The matrix B has a single eigenvector in the eigenspace. To describe this situation using precise mathematical terminology, we say that the algebraic multiplicity of the eigenvalue 3 is 2, but the geometric multiplicity, the eigenvalue is 1. The matrix B is 2 by 2 matrix with a single eigenvector. since we're one eigenvector short, oh yeah, because it's 2 by 2, so it has to be 2 rows, 2 columns, I should say. Now, since we are one eigenvector short, we can't construct a diagonal change of basis Q. We say that the matrix has a deficient geometric multiplicity, meaning it doesn't have a full set of eigenvectors. Therefore, B is not diagonalizable. Now, I think the one thing I'm concerned about is that I don't think this paragraph is specific. Will help you a ton. But considering what properties eigenvalues and nil point matrices must satisfy might... Actually, like, for this question, right, it says diagonalize the matrix. Now, my question is this diagonalizable? Because it has 2 2's here. Is it only when, like, the whole row is, like, basically the same number? Like, the whole diagonal row, the whole diagonal is all one number? Or is it when it's, like, you see multiples of one number in the diagonal? When it's not, diagonalizable. Like, I can't even say it. I think that's the one thing I have to, like, ask. Because I thought this looked funny because it's a multiplicity of 2 here. But then the way it looks, it's like we have a row here, we have a row here, and we have a row here. A matrix is diagonalizable if only and only if the full set of linear independent eigenvectors. So because usually I think it's because I'm so used to solving for the eigenvalues. Like, I think the eigenvalues lead to eigenvectors, but at the same time I'm like, can you just, like, look at the matrix and, like, if the diagonals, like, are all different numbers, does that mean that they're like diagonalizable? And if they have, like, 2 parts of the diagonal is the same number, but yet the other ones are different, does that mean that they're not diagonalizable because they, like, 2 of the numbers are the same? Because it's like a multiplicity of, like, 2 numbers. Because that's what I'm trying to understand here. Because the way they showed the example is that it seems like the whole row is like the whole diagonal is like one number, but for this one we have like one number that's different. So does that mean it's not diagonalizable, or does that mean it but since there's a 4 here, does that mean it is diagonalizable? Multiple of the same number implies that algebraic multiplicity, but not necessarily geometric, but I'm not sure. Okay, so maybe it is diagonalizable then. So I guess we're gonna have to solve for the eigenvectors at this point. Okay, so I guess we're still not done with this one yet, so we're just gonna have to see if it is diagonalizable to see. So if we have a that would have to be all multiplied by a vector v. Or maybe we can make an e. Make it a little bit easier. Then that's all equal to 0. So we'll actually we'll remove this for now, and we'll erase this because I don't think we're quite finished with this yet, because we want to see if we actually get eigenvectors in this. So then we're left with 0, 0, 6, and then 0, 0, 4, and then 0, 0, 2, and if we think about this as, so this one is 3 by 3, which means we need a 3 by 1. So we can think of it as like this. But at that point, if we think about it, then we're left with zeros here, then zeros here, and then we're left with C here, which is 6, 2 equals 0. Ooh. So all these just basically just go bye-bye. And we're just left with one. Meaning that the only way this is 0 is if C is 0. And that would be like, so basically you could have A and B, but C would have to be 0 at this point. So what about like if we have A times 4, A minus 4 I should say, minus 4i. Then we would have minus 4, that's 0. Okay. So if we have that, and we have A and B and C here, then we would have A 0, 0 plus B 2, and then C 6, 4 equals 0. So we have A plus C6, or maybe I should just put 6C, and for the rest we have zeros at the bottom. So it's 4 here. Okay, so the term we can make C equal to B equals a half, and if that's the case, then A plus B equals 0. Which makes this A plus which makes A so for 4 so since both rely on C, why don't we make C equal to 1 in this case? If that's the case, then A plus 6. I probably should have done that at the beginning. Equals 3. Then we have 2 plus 4 minus 4 B is equal to negative 2. So for 4 we can have, so for 2 and 4, so for 4 we can have a basis vector of 2 and then 1. Now for this one, I mean A and B could be any value, so we could probably give them 1. And then we can make it, because practically we have zeros here, so. And we have 2 2s, so does that mean we have, so it's basically our basis vectors are like this. I mean, it does give us 3 basis vectors. I mean, like 3 eigenvectors when I think about it, because this one is just done twice. But I don't know if that's truly what counts here. I bet like looking at all this looks like a total mess, huh, guys? What's your intuition on diagonalizability? Is so important. What's the core feature of diagonalizable matrix? I don't even know if I have an intuition, to be honest with you. I mean, like, the way it is like... I mean, part of me feels as if, like, we did have, like, the eigenvectors that we wanted, because it's basically 3 by 3, and we really wanted, like, 3, and, like, the way it looks like in here, we do have 3 rows that basically gave us, like, a diagonal. The one thing that I'm unsure about is that I don't know if, like, since it does have an algebraic multiplicity, I am not quite particularly sure if this is diagonalizable or not. But the way it looks like, the way we did this problem, or like the way we expanded on it, actually, it feels as if it is diagonalizable. But I don't know if that's completely correct. Because, like, the one thing about me is that sometimes I think I have an idea that I know something, but I don't know if I'm misconstruing it with my own intuition. That's the one thing. But then again, probably I shouldn't keep questioning my intuition that much. Because I'm so used to people telling me that I'm thinking the wrong way. But then again, that doesn't allow me to think for myself sometimes. Maybe it's just me being a perfectionist at this point. Because, I mean, if this was diagonalizable, this whole stream is just me trying to pronounce that word. It feels as if this kind of makes sense if it does have an algebraic multiplicity, but we are trying to match it with the geometric multiplicity. It feels as if, like, this could be correct to give us, like, I guess this is the eigenbasis. So the important thing to remember is this: a matrix is a transformation. Diagonalizable matrices can be written as a matrix with all the values on its diagonal. That means, crucially, that no vector other than the 0 vector can be transformed to the 0 vector. The kernel of the transformation is the 0 vector. And that is important part, knowing what these matrices do. Okay, like, now I gotta break apart what you just typed up, Ursula. So yeah, matrix is a transformation. That I understood. Diagonalization can be written as a matrix with all the values on its diagonal, okay? That means, crucially, that no vector other than the 0 vector can be transformed to a 0 vector. The kernel of the transformation is 0 vector, and it's an important part of knowing. So when you check which matrices are diagonalizable, you basically check if there are any vectors that can be transformed to the 0 vector or not. So if v equals 0 only if v is equal to 0. Okay. So I'm guessing because we got these vectors here, does that mean that it's not diagonalizable? Because I remember the last time I did these problems, I got very fidgety with well, where was it? I know it was here somewhere. Not this one. Oh yeah, this one. This one basically had like a lot of like terms that crossed out, and I couldn't basically write a vector for it. But then again, they all equal 0, which fits. And basically the only way to get this matrix to equal 0 in this case is to basically have a 0 vector in there. So I'm guessing that maybe because what we did on this section, where is it? I think it's right here. Yeah, right here. Then maybe it's not diagonalizable because we got like vectors like this, I think. So I guess my intuition was correct because we have a multiplicity here. I guess I just wanted to see if I can deconstruct this. Do you say that you do that by saying, hey, let's check what this matrix does to its eigenvectors if its eigenvectors span the whole coordinate system and are linearly independent, and you express the matrix as how it acts on the eigenvectors. That means no eigenvectors can cancel each other out, so to result in a 0 vector, and you can only reach the 0 vector if you plug the 0 vector. So is what I'm saying correct, or am I just missing am I still missing something? Because I feel like that the only way that like what you're explaining to me, Ursula, is that if we get eigenvalues but they give us like vectors that are not the 0 vector, then that means they should not be diagonalizable. I mean, that's what I'm getting from what you're typing, but I don't know if I'm misunderstanding. Because like I remember my experience with the first couple problems here. Yeah, with these. And I know that I couldn't get A and B because the terms that I was getting would cancel each other out. And basically it would be 0 equals 0. So I couldn't really get eigenvectors that way. That's not true. Okay. Like now I'm like very confused. Because I don't even know if my intuition is right or like I'm completely lost. Because I know you guys are also like when you guys are giving me like hints and stuff, like I understand it's basically just to help me develop the intuition, but like now I feel like my intuition is completely way off. So I don't know which parts of my intuition is correct and which part of my intuition is not. That's the one thing. But then again, I'm probably thinking of this as doing an algorithm, which I probably shouldn't do because math is all about proving stuff. Okay, no problem. Grandma Ursula, no problem. Actually, also, guys, if you join the Discord and you basically have a Twitch name or a YouTube name that is different from your Discord name, it would be helpful for me if you actually were able to, like, I wouldn't say change your Discord name, but like if it's in our like MathSpellBook Discord server, and if you guys want a link to that, it's in the description down below if you're watching this on YouTube. But in Twitch, I will type it in for you guys for the Discord. Let me see here. Oh, that's odd. I can't even type in my Twitch chat. What the heck? Well, I guess the Discord server popped up for me. Yeah, if you're watching this on Twitch, like, you know, like, if you access our Discord server, if you go by a different name on Discord, it would really help me out if you were able to, like, show your display name on the Discord server as your Twitch name, so that way I can know that I'm talking to the same person. Just for reference. Linear algebra is all about transformations and geometry through, and when you get into the weeds of doing algorithms without knowing how diagonalization really behave, you can get lost really quickly. Okay. I mean, that's fair. Yeah, because now, like, because I mean, the way they state it in this book, it's something that I can understand, because it's like, okay, so these two threes, they repeat, and thus they have a different multiplicity, algebraic multiplicity of an eigenvalue 3 is, so it's like 2 of them, but its geometric multiplicity of eigenvalue is 1. So I'm guessing that because it has 1 eigenvalue, and since we have, like, the last example we had was that it has two twos, then that means it has 2 numbers as, like, the geometric multiplicity, if I think about it. So in my mind, I think it's not diagonalizable because of that, but at the same time, I don't think that I'm guessing what you guys are telling me is that that's not accurate. That's not accurate of actually, like, how to think about that, which is actually making me more confused. And this is a 2x2 matrix, but the other one we have is a 3x3. That's the one thing that I'm, like, also thinking about. No, it's okay. It's like, basically, I feel like I'm, like, looking for a yes or no answer to basically to know that I'm on the right path to somewhere, but I think the details are not as the explanation is probably not as simple as that. But at the same time, I know that, like, with math, math and physics, you have to struggle a bit. But at the same time, I'm like, I don't know what the extent of that struggle is. Such as, like, oh, I have to keep banging my head to the point where it's like, I feel like I'm not getting anywhere. To the point where maybe I have an idea and then suddenly I have a revelation. It's not, like, for me, I try not to be the rage gamer where it's like, why doesn't this work? This should work. Like, you know, this is dumb. Why is it that what I'm doing, it should work, but it's not working? You know, I don't want to be that type of guy. So like for me, it's like I always think that the problem is always like from what my thinking is, and that's the reason why it's like I guess it feels like I'm kind of like yelling in the abyss, but at the same time it's like I'm not trying to shout at it. It's more like I'm trying to gauge with it. I'm trying to gauge with whatever it is that I'm lacking. It's just that I'm not getting a hint of exactly what is it that I'm missing, as well as what is it that I'm overlooking. So I'm pretty sure there's some parts of my thinking that is correct, but it's not completely 100% there yet. Like 100% to the full understanding of what it is. I know that's getting into the like the deeper philosophy of like, you know, being stuck on a problem, but at the same time I think when I talk it out a little bit more, it allows me to organize my thoughts a little bit easier. Like I know why I'm getting confused. It's just that I don't know what the technical details that I'm lacking is it that's leading to my perplexity in the issue or the subject matter. That's usually how I am. I just philosophize everything because I know, like, you know, complaining about my inability to solve a problem won't solve anything. So I basically have to generate, I guess, a mental map for myself to actually say, like, it's okay to be stuck like this. At the same time, to fight my ego, to basically say, hey, like, I'm not the smartest person in the room. If I don't get it, like, you know, like a lot of people probably wouldn't get it. Which I understand why people get into rabbit holes when it comes to subjects like physics and mathematics. Like, the mental fortitude is real. I barely even have a knowledge of calculus, so it's like I don't want to get mad at the things that I can't solve, because if I get mad at the things I can't solve, then that takes away my energy of actually trying to find ways to actually navigate them. But of course, like, when the problem has a solution, you feel as if, like, wow, people have already solved this. Why is it that I'm so inadequate? But at the same time, like, I think that feeling has to come no matter what, especially when you're dealing with a very academic subjects like mathematics and physics. I struggled at this stuff as well when I learned it. Yeah, everyone struggles with it, I think. I think also the struggle always is going to be there. I think finding the right source to actually explain it in a way that you understand is always going to be the pursuit of it. That's why I keep going to the books that I've used a lot, because, like, whenever I read other books that, like, maybe you guys recommend, sometimes it goes over my head and I'm like, or the text is not set up right in the way that I can read it. So I basically have to go back to the basics of what I'm used to, which is why I probably buy a lot of books. My dad, like I actually got a book in the mail yesterday, and my dad, like, I have a ton of books in my room, and my dad would always ask me, why do you buy so many books? And, like, part of me felt like, because my dad is like my dad knows how to fix electronics, but he's a typical, like, dad that basically loves sports, and he loves doing handiwork, and he loves to work things with his hands. But he's not really someone that's, like, into, like, academics. Like, he likes science, but he's not really into, like, you know, reading textbooks and all that stuff. And, like, when he asked me, like, why do you buy so many books? It's as if, like when my dad asked me that question, it felt as if he was kind of like, why do you waste your time reading so much? It kind of felt like that to me. Please give me give me basics. Can you tell me what are vectors? Why do we need them? Oh, hello, Stardust. Actually, I like that name. Welcome from YouTube. Yeah. So I guess we can, like, take a break from this. So vectors, the best way to think of vectors as, like, how should I explain this in a, like, Stardust, like, are you more physically minded, or do you want like a mathematical explanation of what vectors are? Because mathematically speaking, vectors are a bit more complicated. Can you please tell me why do we need them and their relationship with is that metrics or matrices? Stardust. Because I don't know if you wrote metrics or matrices. Just clarify that for me, please. So basically, Ursula, what you typed. So basically for this, you want to check if the algebraic multiplicity and the geometric multiplicity for each eigenvalue, algebraic multiplicity exponent of the eigenvalue in characteristic to polynomials. That I know, yes. The geometric multiplicity dimension curve. Oh, the kernel of A minus lambda and the identity. Okay. I like taking knowledge. Okay. So basically for physics, you have to think of vectors as a number with a direction. So let's say if we were to throw a ball, we have a vector that goes like this. So let's say this vector is the speed of the ball, and the way we think of balls, we know that they go in a parabola like this with some angle theta. All right, so mostly vectors, you have to think of them as an expansion of just like regular numbers. So there's things called scalars. Scalar is just a fancy way of saying a number, basically. So it's just a number. So it could be like 1, like 0, 1, 2, and da 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 da. But they don't really like, they only signify things like, you know, like a value, but they don't really have that much besides that. Now for a vector, you have to think of a vector, like the best way to think of it in like, you know, our physical world is that it's a number with a direction. So this is where like trigonometry comes into play. So that's why you learn things like sine of theta, cosine of theta, and I mean sometimes you can think of tangent too, but like tangent rarely comes up sometimes. I usually use tangent whenever I'm solving for a shadow problem. Like if you have a pole and it casts a shadow right over here, and the sun is beaming on the pole to create the shadow at a specific angle. Oh, I gotta get rid of that. Like, yeah, there we go. So the sun, let's have the sun up here. So the only time I would use tangent is that we know the height of the pole and we know the length of the shadow, and then basically we get the angle of where the sun is, and then vice versa. I just like, that's the time I usually use tangent, but it's not really like a, I guess you can think of it as a physics problem, but it's more like just a mathematical exercise. But for physics, on the other hand, vectors are just a good way of writing forces, because forces, they push things. So when you have a force, if you push on something, it moves. So that's the best way I can describe it, unless you want to see an example. Hopefully that helps. So we're eagerly waiting for your answer. No teacher could explain it to me. Why do we need them? Well, the thing of it is that it depends on what you're going to get into. So if, like for me, I like physics, so the reason why I think vectors are important, at least for me, is that they talk about how forces behave. And there's things called vector fields where like you have a bunch of vectors acting like in a specific area of space. And when you think about it, you can think of it as like, you know, when you take a shower and then the water goes into a drain. When the water goes into like the drain to drain out your tub, it's basically a vector field. So it's a bunch of vectors pulling the water into that specific point. So that's one of the reasons why I think vectors are important, at least for me. But depending upon what path you want to go on, like studying math or like for any specific purpose, sometimes you just have to find the thing that connects with what your interests are, or what is it that you wish to implement them with. If you want to build video games, you need vectors, because you obviously want, like, if you're building, like, say, a game that involves like shooting or like projectiles, you want to make sure that everything flows with the laws of physics. Like, you know, like if you're like making a game like Call of Duty or something, like, you obviously want the bullets to basically go straight. And you also want to make sure that the gun, to make it more realistic, you also have to make sure that the gun has recoil. So then you can create a vector for recoil of the gun, if that makes any sense, because it involves like Newton's laws of motion. Yeah, I gotta learn vectors. Hey Famish, how's it going? Can you give me an example, please, of other usefulness of vectors? Sure. I'll do my best to, because I am not a teacher. But I'll try to. So, like, I mean, what type of example do you want? Because the thing of it is that the first example I can think of is just you throwing a ball at a certain velocity. And when you throw the ball or kick a ball, like if you like football, and when I say football, I mean soccer. Like if you kick a ball, it will just go into an arch like this. And what the vector is basically the, I don't want to say the speed, it's the velocity, because velocity and speed are different. So speed is just basically the number, it's the scalar, it's basically the value of the velocity, whilst the velocity itself is the speed and the direction. So understanding vectors, you also want to, like, if you want to do like fun stuff, like involving like science experiments, such as a good example would probably be like if you were driving a car, right, and you want to be able to measure, because I'm thinking of action movies. I don't know why I'm thinking of action movies, because I was actually watching an episode of Mythbusters like before our stream. If you really want, like, I think the experiment they did in Mythbusters is that well, bad guys are chasing you, you can shoot a gun and it will ricochet underneath the car and go through the floor of the car. So vectors are very important in this scenario. So like if you were to shoot a bullet, it will basically, depending upon the angle you shoot at, which is a vector. So like you would have like a angle right here. You have to basically judge the angle and and based on that angle, you can basically determine how much it will ricochet off the ground. So it's not very a useful example, but if you really want to basically make vectors useful for you, and it's the best way to do it is by doing like weird fun stuff, I guess you can think of it. I don't know if that helps you, Stardust, but hopefully that kind of inspires you to see the usefulness of vectors. Like if you want to actually like bounce something off a wall, like using a bouncy ball, that's also another way to see the usefulness of vectors. Like if you were what's the game called? I think the game is called I think it's called handball. I don't, because I was thinking of also squash. That's the reason why I was thinking of two names. Whenever the ball bounces against the wall, like that's a vector. So like the more force you put into the ball, you also realize that the number of the force, like basically the number that indicates the force, like say if you do a force of let's say like 10 newtons or something, Like, I know I'm just basically putting a number out there. That's probably way too high, but if you were doing a force with that type of number, you also know that there's also going to be a direction associated with it. So I hope that helps. No, I'm not a teacher. I'm just a hobbyist. I just like math and physics. That's all I do. Because I know a lot of people, when they see like people that have math channels on YouTube, math and physics channels, it seems like they're teachers that already have like PhDs. But for me, I don't have any like certification for that. I just basically tell it the way I see it. That's the reason why I think I get details wrong sometimes. But I try my best to explain it if I am used to it. No, I'm not a teacher though. I just like explaining things. Like, I try to explain things in a way that relates to another person, because I don't know what your guys' interests are. So, like, I try to connect the material that I know, and if you want to learn it, then I try to connect it with what makes your life important for you. Because, you know, I could basically tell you what I find is important about the material, but that's not going to inspire you to do the thing that you want to do. If that makes any sense. Because some people like computers, and I don't know anything about computers, but I'm willing to learn it with you to actually like implement it so it's useful for your life, you know? Yes, I've heard of Ramanujan, yeah. Well, why you ask, Stardust? I know Ramanujan self-taught himself, which is very, very impressive. The only thing he had to learn from like Cambridge, I think. Was it Cambridge? Now I have to Google it because I want to make sure that I'm accurate with information. Because I do know about some mathematicians, but not their history. Was it Cambridge or was it another university? Or was it Oxford? Trinity College. Okay, where's Trinity College at? Cambridge. Oh, it is Cambridge. Okay. Yeah, because like it's impressive that he taught himself. The only thing he had to learn from Cambridge was basically how to do mathematical proofs, which is not easy. It's not easy to learn that. I mean, I'm trying to learn it now, and I feel like I'm barely getting by with it. The dude had never seen before insights about math that he dreamt about. I like how sick that is that you dream about novel math proofs, then say, my goddess told me that. Me from India, he's my ideal. Oh, okay, I see. Well, that's good. So that means you like math. That's also good. But yeah, like I think a lot of people from India love math, so I'm very surprised that sometimes I would get like some people from India asking me for help, even though I'm not really certified to teach. I just like math and physics, but of course, like I feel bad for people that are looking at math channels and they're expecting someone who is already a teacher to help them with their stuff, and I'm like, I'm sorry, I'm not a teacher. I'm from the U.S. I know Stardust, you asked me that, like where I'm from. I'm actually from the U.S. He says God teaches him math. Right. I'm not surprised people from India love math. Yeah. Yeah, but I'm from the U.S. On the East Coast. So, like, I think for me, if I knew my love for math during high school, I probably would have been like very insecure about myself still, because I would have to basically try to build myself as this smart, intelligent person, even though I wasn't. I'm just someone that just likes the subject, but I know I struggle hard with it. Like both subjects, actually. You know what? I feel like we can probably do some physics questions. What let's see, thinking physics. Let's open this up. I usually love this book. I did problems from this morning, but this one I got right. I was actually very surprised of myself because I was actually thinking about this one. This one I got wrong because I was like, what are they asking for in this question? Because like maybe I'll let you guys do it. Like, because I got this wrong because I didn't understand what the question was looking for. It basically says a hurricane. The force exerted on a house is 120 miles per hour. Hurricane wind is A equally, B twice, C twice, and D 4 times as strong as the force exerted on the same house by 60 mile per hour gale winds. Now, the reason why I got this wrong is because I didn't understand exactly what the question was looking for or what the subject matter was. That's the one thing that I kind of got a little bit iffy about, because I was like, what is the question asking? It's telling me that there's a force, but what is it that you want me to reply to it? Is it like, am I supposed to know things about the force? Am I supposed to say Newton's third law? Like, I wasn't sure exactly how to interpret this question. But yeah. Like, I mean, like, if you guys want to actually give a crack at it, like, tell me what your answers are in the chat. And I'm pretty sure a lot of you will probably get it, because for me, I got it wrong because I was thinking of Newton's third law, but I was like, no, that probably is not what it's asking. I'm debating of I should get a bachelor's degree in math. Certificate doesn't matter. It's about passion and how I feel. Yeah. I agree. I think nowadays a lot of people are realizing that university degrees, they're really good when you want to expose yourself to people that are in the fields, like, you know, professors and stuff. Especially for like academic fields like physics and mathematics, as well as like, you know, the scientific pursuits. But I think universities are now like, I think now they have to basically have to stop marketing themselves as people that provide jobs. Because people go to university for one purpose and one purpose only, and I will say this right now, you only go to university to go to grad school. That's the only reason you go to university, or just to educate yourself. That's the only reason I think you should go to university. If you just want to get a job after high school or something like that, just get a job. if you just want to make money, like, that's basically my take on it. Now, of course, like, if you just want to like take a year off to give yourself like time to think about what you want to do, take a year off and think about what you want to do. I would say, like, take that time for yourself. And then, like, if you want to go to university and say, like, oh, I want to do something in the sciences, or I want to do something in the medical field or something like that. Like, when you're certain that that's what you want to do, then you basically just pursue that. And if it doesn't work out, then you can basically try to see if the place that you go to has like different pivot avenues that you can do. Because I think that's the thing that universities have, is that if you major in something and you don't like it, you can pivot to something else. And I think that's the thing, that's why it's worth going to university. It's just to educate yourself. But a lot of people just go to university just to get a job. And I think that's the wrong reason to go to university, in my personal opinion. Technically, a tech employer is only looking for your portfolio. Yeah, exactly. So, like, even for like computer science, it's probably like kind of like I don't think it's a waste of time, because it's kind of good to like learn from like institution about technology. But at the same time, if you really want to build apps and you really want to actually put your name out there as like a programmer or something, yeah, you have to build more stuff while you're in school, and that's like a lot more work on your part. To be honest, the Indian government schools lack good teachers. Oh, really? With like a lot of like people that are interested in math in India, I thought they would have like really good math teachers and good physics teachers too. Like, actually, like when I watch on YouTube, like I've seen like some teachers from India. Some of their stuff is actually pretty good. Like, it's in English. Like, I usually watch it in English though. So did you guys think of the answer to this question? Like, what's your response, guys? Is it A, B, C, or D? I mean, I'll tell you the answer I got, and it's obviously wrong because I was thinking of Newton's third law, and I was like, no, that can't be right. But actually, Stardust, is there anything more you want to ask? Is D? So that's your response, Famish? Well, the answer is you're right. It is D. So, for those of you who actually got it, what is it that the question is looking for in this case? It is D. You were correct. You were correct, Famish. Yeah, the one thing I think I got lost at was that what was the question technically asking? Like, I wasn't sure exactly what this physics question was asking in this page, because it just says the force exerted on a house is like 20 miles per hour hurricane winds. So was there like I don't want to think in the terms of formulas, because obviously physics is physics. I guess because you can't really think of the equations when it comes to physics. You have to actually think of the physical nature of the system in general. Because according to this, it says D 4 times as strong as the force exerted in the same house by a 60-mile-per-hour gale wind. Now, the way they explain this, I understand what they're saying, but at the same time, I'm like, I didn't feel like I have a clue exactly what exactly is it that they were trying to explain here in this. Like, what is it that they wanted me to actually think about here? Because, I knew the wind, hurricane winds are, very powerful and stuff, but how am I supposed to think about this particular problem, you know? And it's usually stuff like that I basically ask myself when it comes to thinking about a problem, because sometimes I think about a problem it's a problem where you sometimes ask is there a difference between tension and forces? And apparently what I learned from this book is there is a difference between tension and force. So because I know I got a lot of problems involving tension incorrect, because I thought of force and tension as sort of the same thing, when actually they're not. Yeah, so I think we're still pretty lost when it comes to diagonalization. Maybe ChatGPT can help me with my misunderstandings of the material. So okay, let's type this question: how to tell if a matrix is diagonalizable without computation. Let's start off with that. I sometimes use ChatGPT to basically answer questions for me. Not answer questions, but to basically help my thought process. Because I feel as if once I give my question or my thought, the way my thoughts are structured in ChatGPT, it feels as if it kind of helps me navigate exactly where the weeds I'm getting into don't work. Which I think that's what AI is going to help us with when it comes to whenever we're getting stuck on a problem or something like that. Let's see. Without heavy computation, relies on theoretical properties. Okay. Theoretical rule. Has n linearly independent. So basically, a square matrix is diagonalizable if and only if n linearly independent eigenvectors. This is equivalent to the... Okay, yeah, it's just exactly as you said, Ursula. So let's take a look at our example before. So right here, no, not this one, right here. So technically this would be algebraic multiplicity of 2, because technically we have like 2 answers here. We have 2 and 4. Now, according to ChatGPT, we would have to figure out what the geometric multiplicity is. And I mean, given the way it's like, when I think about the dimensions, the dimension of the column space, I feel like it's 3. So that means we have 2 with 3, which is not, which kind of makes it feel like it's not diagonalizable. I'm not gonna get used to saying that word ever. I always get tongue-tied when I try to say it. Let's see, situations where a matrix is definitely diagonalizable. Matrix is symmetric. Oh, that's a new one. Hermitian complex. Okay. Okay, here we go. Warning signs that matrix might not be diagonalizable. Defect matrices are not enough eigenvectors. Okay. If an algebraic multiplicity, an eigenvector is greater than 1, and you suspect that geometric multiplicity is less than, then that might not be diagonalizable. Join block. Okay. So I think my question for ChatGPT in this case is, if a matrix with let's say a matrix that is n by n have 2 entries in the diagonal that are the same number, does that mean the matrix is not diagonalizable? Okay. Okay, that's a good example I was looking for. If a matrix repeats a number in a diagonal, it still might be diagonalizable. Okay. Depends on the eigenvalue vectors and just the values. Okay. This matrix is diagonalizable. It's already well, yeah, it's already structured this way. When eigenvalues are a problem, okay, so if it's like this, so basically if it's like the whole thing is like one value, then yeah, it's not diagonalizing. That makes sense. Key takeaway, repeated diagonal entries alone do not determine diagonalability. You need to look for the eigenvectors, okay, in N. So matrix is diagonalizable even if eigenvalues repeat, as long as there are enough eigenvectors. Okay, so when we did this one, So we had like two, so we would have to say that we had like two algebraic, I don't want to say multiplicities, but we had like two entries here. And we also have two vectors here, so we don't really need, so I guess this is diagonalizable at this point, based on what it said. So I guess this is our eigen basis here. So I guess we did learn something. That's good. I know, like, it seems like whenever I use ChatGPT, it seems like it's kind of like a cheap shot, because it seems like I'm not learning by myself mainly. I'm just relying on an AI to like explain something to me. But I try to use the tools that I'm given. Like, for me, I never want to put like the problems I'm working on into ChatGPT unless I don't fully understand the explanation of the solution. That's when I get a little bit like I feel like I'm cheating at that point. Actually, maybe I should put this on ChatGPT. Like, ask like, what is the question looking for in this case? So. Copy. Oh, no, not that one. There we go. Let's paste. Let's see, this question is testing your understanding of how wind speed affects the force exerted on an object. Especially using physics and fluid dynamics and drag forces. What physics concept is being tested? The force that wind exerts on an object like a house is primarily due to the air resistance and drag force. And the equation for drag force is O. Okay, so yeah, I haven't done any problems involving drag force, as far as I remember. Let's see, force is equal to half the air density, the drag force, and then the area hit by the wind. Sorry guys, excuse me. The key insight, the force is proportional to the square of the wind speed. Oh, okay, I guess that, I don't know if it's something I learned before, but that's something new. So, learn something new every day. So I guess when it comes to wind, we have to like keep, we have to remember this relationship. So the force is proportional to the square of the wind speed. So if you double the wind speed, the force is quadrupled. Applying to the question, hurricane is 25 miles per hour and the gale is equal to 16 miles per hour. So the wind is twice as fast as the gale wind. Now apply the relationship. Actually, come to think of it, I don't even know what a gale wind was. Let's see, force of a hurricane. Okay, so the force of gale winds. So the force of the hurricane winds and the force of a gale winds. So, it's 4 times. So the force of the 120 mile per hour winds is 4 times as strong as the 60 mile per hour winds. So the correct answer is 4. Yeah, I got the same one. Recognize the question is about wind force drag. Recall the identity, the formula. Okay, so it's a question that involves something that I'm not too familiar with, which is good because it allows me to actually learn a little bit more to figure out what exactly the solution is. So when it comes to like wind and drag, I have to think about this relationship. It's proportional to the square of the speed. Interesting. Let's see if we can do the other. This one I haven't done. So, oh crud. Let's see. I'm trying my best to like. I feel like I saw the answer, but I'm trying to like basically block it out of my head. Let's see. Rocket sled. A little sled weighs 1 pound. It is set in motion over frictionless ice. Okay, so we're dealing with frictionless surfaces, so that's something that makes it easier. By a toy rocket motor. After the rocket fuel is extended, the sled is coasting over the ice at 1 foot per second. Okay, so that gives us a velocity. So 1 foot per second. How much force did the rocket exert on the sled to make it go? Okay. So how much force did the rocket exert on the sled to make it go? Okay. So we have a sled that weighs 1 pound. It is set in motion over a frictionless. Okay. After the rocket fuel is expended, the sled is coasting over the ice 1 foot per. Okay. So this is a force question. So how much force did the rocket exert on the sled to make it go? Okay, so since it's frictionless, let's see, 4 pounds, 16 pounds, 32 pounds. So I think we'll take this. Oh, no. I gotta do that over. So, okay, let's do that. Bring this down. Paste. Because sometimes I like to write out stuff whenever I do these problems. Okay, so the mass of the sled is 1 pound. We'll just put 1 pound. But I do want to convert that though. But then that's 1 pound of force. And then we have to convert that to newtons, and I'm not going to be looking forward to that. Yeah, we might as well convert it. So, pounds to newtons. Wow, 4.44. 4.5 newtons. We'll just make it that way. Okay, it is set in motion over frictionless ice by a toy rocket motor. So, how much force did the rocket exert on the sled to make it go? Okay. So we have a velocity of 1 foot per second. So now we have to think about the relationship here. So what I'm thinking about is force times time. and that over now. The problem is we don't know how much time it took for the rocket to go. Let's see if there's anything in the question about that. No, there's nothing about that. So we don't know how fast the rocket was going. So what we can do is use this equation. Acceleration to x, but we don't know what distance it traveled though. The initial velocity will probably be 0, and the final velocity would probably be like 1 foot per second. Well, if the sled weighs 1 pound and that's usually like if it's like standing still on the surface and you have a rocket that propels it, unless the rocket is attached to the sled. I mean, because I don't know if it's counting the rocket as part of the sled. So we have to have like 1 pound of force to basically move. This is the reason why I like these problems, because they make you think, and I'm like, what is it? What is the details that I'm missing here? Because the way the sled is like my drawing is very crude. Actually, I don't like the way that is. It looks like a boat. There we go. So we have the rocket here. Okay. Now, I'm guessing that we have the normal force here, and the force of gravity here. So this is the mass times gravity. Now, in order for this to move, we actually have to have like a force that's like pushing from this side, which is the force of the rocket, which is equal to force times acceleration. Now, so the rocket keeps going until it loses fuel, and then the sled is moving. The sled is moving at 1 foot per second. So does this have to do with work? Like work done? But then again, we don't know the distance of how far it traveled, though. Let's see. We have 1 pound, 4 pounds, 16 pounds, and 32 pounds. There's no way to tell from this given information. I don't think it's D. I mean, I don't think it's E. So, because I think if it's 1 pound, because we have a frictionless surface. And it goes 1 foot per second after the rocket fuel is used up. So I'm guessing it has to travel very fast, but not too fast. So I think 32 pounds is out. And I think 1 pound is probably not enough. It's like... So it's either between C or B. I think I'm gonna go with C. Because when I think about it, we also have the normal force and gravity. And like I know with gravity, it's like, I think it's 32 feet per second. And with pounds, because like obviously 32 pounds I think is just way too much. It'll probably like make the sled go careening very fast. I think C. I'll go with C. Let's see what the book says. Oh, the answer is E. Usually with this type of answer, I would think that it's just something that makes you think it's not the answer. Oh, okay. I guess I got tricked. Because usually when you see this, I always think that it's not an answer, because they want you to solve it anyway. Okay, so why is it E? You can't tell. The rocket motor might provide a small force for a short amount of time, big force for a short amount of time, but the information given to you can't tell. This question is very much like asking how long is a rectangle which contains force. Okay. It might be one long... Okay, so let's give you an example here. In the case of the sled, its momentum is like the area of a rectangle, and the force and time during which the force acts are like the size of the rectangle. Okay. Although the forces and times are different, in the 3 cases, the momentum each produces is the same. Interesting. Well, sometimes the answers you think are just silly answers, they could be the actual answer. I guess that's a good way to end stream. Just because there's something that says there's not enough information doesn't mean it's not an answer. Hopefully you guys learned from my mistake. Okay, I think that'll do it for today, guys. Thank you for joining me on today's stream. We will be back next week to do more math and do some more physics as well. So if you guys are watching this on YouTube and you like physics, math, as well as like, you know, having a study stream to interact with and basically like do your projects on the computer, as well as probably like at your study desk, you know, feel free to drop a sub. And if you're watching this after the live stream airs, put something in the comments down below, like what I can do to improve or what problems you think I should check out. In addition, hit the like button if you're watching this on YouTube. And all of the links will be in the description down below for our Discord server, my video game channel, as well as my Twitch channel. And if you're watching this on Twitch, you know, drop me a follow. It's much appreciated if you like math, physics, as well as, you know, just having a study stream in the background just to keep your guys productive. But yeah, that will be all for today, guys. I will see you next week, and always remember, everyone is precious. You guys are just as precious as everyone else, and I will see you guys in the next stream. So take care, guys. Bye-bye.